there is a branch of complex analysis and everyone knows about it. So what is analyticity and singularities? So basically, suppose fz be a complex valued function. So simply knowing being a function, one can know about its limit at certain point, its differentiability at some point, and its integrability. So since I'm prepared a presentation on analyticity and singularity, so today I am going to discuss how a function actually behaves in some neighborhood of singularities after being analytic. Okay, so myself Surjan Narayan, working as an assistant professor in PG Department of Mathematics in Berhampur University, and I have done my NSc from Banaras Hindu University, and then cleared my GATE examinations in mathematics in the year 2023. So before going to discuss this entire topic, I have planned my talk in the following ways, having these following contents. The contents are nothing, there are some notations, there is some definitions, and another point is on regular points, analyticity, types of singularity, and conclusion. Now, actually, my dears, when I take class, I am asking to my students whether this term complex present in this word complex analysis makes the entire analysis complex or not. So most of the time I am getting the answer that sir, yes. Actually we are feeling this analysis makes complex genuinely. But actually I am thinking that this complex analysis is not that much complex. By simply seeing the word complex present in this word complex analysis doesn't make the entire analysis complex. In fact, after reading means the same stereotype I actually with me. So when during I am doing my graduate studies, I also thinking like this, that complex analysis must make the analysis complex. Okay, but after reading analyticity and singularity under the guidance of Dr. Kanhalal Mahato sir in my university, I think that complex analysis is not that much complex but much we think. Okay, so before doing all these things, first of all I am telling what actually complex analysis does. In day-to-day life, the students who are already reading in physics as their honors or chemistry, there is a talk or there is an equation that is Schrodinger's wave equation. So during the entire derivation of this equation, there is an application or in fact the first application of complex analysis. So if anyone thinks complex analysis is complex and he or she is studying physics or chemistry, so he or she must have trouble during the proof of the Schrodinger's wave equation. And this is not the last example. In fact, we have more than one applications in our life also where complex analysis is used vastly. Now, after doing all these things, I am introducing what complex analysis actually is. So complex analysis is nothing but a vast branch of mathematics that deals with functions of complex numbers. Generally, everyone knows what are complex number. Everybody knows about it. Any number of the format z equal to x plus iy, where x and y are real numbers. They are, or in case this I equal to under root of -1. And the complex plane is called Argand plane, you all know. And for any input z, there are some complex functions, they have more than one values. But in case of real analysis, for every input x, for the function y equal to f of x, we are entitled to have only one output. And that output is always unique, if it is a function. Since I have already assumed that y equal to fx is a real function, so for every input x, I must have only one output. But see the beauty of complex analysis. Here, for a certain input or unique input x, I may have more than one outputs. Such type of functions are said to be multi-valued functions. But a similar analogy is not available in case of real analysis. Okay, because since I have already told you that for any input for a real valued function, I am only going to have only a single number as output. So since I am doing here, or since I am dealing here with complex analysis, so complex analysis explores the properties and behaviors of complex functions, which are functions that takes complex numbers as input and produce complex numbers as output. See here, there is a term complex numbers as output, means this stanza actually gives an idea to us that there are complex functions which are multi-valued. Okay, and these functions can be thought of as mapping from complex plane as a two-dimensional plane, and this plane is some sort of similar to the R2 plane, not actually the R2 plane. Okay, and complex analysis has applications in many areas of mathematics, like as I told you about the Schrödinger's wave equation in case of physics and chemistry and other branches of science. Okay, so after doing all this is my introduction, I am now moving towards my next slide. So please. So there is some actual notations to read, because every time if I am repeating that C is complex plane and any set of natural numbers, D is domain, and this nebula square, which is same thing as dou square upon dou x square plus dou square upon dou y square. So this may be creating some anxious task to my students or to all of you also who are present in front of me. So in order to avoid this type of inconvenience, I am already listed that these are notations where C represents the complex plane, and is the set of natural numbers, D is the domain, and this nebula square is called the Laplacian operator, and NBD stands for neighborhood. Okay. So next slide. So before reading or before preparing talk of analyticity, I am now going to discuss what is differentiability of a complex valued function which is defined on some domain D. Let fz be any complex valued function, and consider a point alpha equal to which is of the format a plus ib in this domain. Okay, and I am already entitled that this point alpha is a limit point of this domain, because if I am not choosing this alpha to be a limit point, actually I will not get any path through which I can approach to this alpha. So after considering that alpha, which is already a limit point, now I am defining the differentiability of this complex valued function fz at the point alpha. So how this is defined? Means for any complex number f of z which is defined on domain D is said to be differentiable at the point alpha, which is of the format a plus ib, is nothing but limit z tends to alpha f of z minus f of z naught upon z minus z naught. This exists finitely. So if this limit exists finitely, for the time being I am denoting this limit to be f prime z naught. Okay, that is f prime z naught equal to limit z tends to z naught f of z minus f of z naught upon z minus z naught. So this definition can also be remodified by means of epsilon delta definition. That is, if a function f of z is said to be differentiable at the point alpha, which is a limit point of the domain on which this function is defined, like the following way, that is, for every epsilon greater than 0, there exists a positive real number delta such that the absolute difference between f of z minus f of z naught upon z minus z naught minus f prime z naught, this absolute difference can be made as small as we please. That is, this absolute difference is less than epsilon for all z such that 0 is less than z minus z naught less than delta in the domain D. Okay. So after introducing the concept of differentiability, I am now moving forward to define what is a regular point for a complex valued function. So if fz be any complex valued function, this is for the time. Okay. So now, suppose I am taking a point, say z0 in the domain D. and this point z0 is said to be a regular point for the function f of z if and only if there exists at least one neighborhood that can be constructed around this z0 in which f prime z exists entirely. Means every point of this disk is going to be a point of differentiability for the function f of z. That is, suppose this point, if means in summary, suppose I am giving a point say z0 and I am entitled to check here whether this z0 is a limit point, this z0 is a regular point or not. Okay. So since I am checking differentiability at that point, it means I must have that this z0 is a limit point. Okay. So after confirming that this z0 is a limit point, now I will check, means I am considering the entire neighborhood, whether this entire neighborhood is a neighborhood of differentiability for the function of z or not. And if this condition satisfied, then I claim that this function has a regular point at alpha. Okay. So now see the definition. So definition is let fz be defined on a domain D and z0 is an interior point in the domain D. Then we say that fz is regular at z0, or this z0 is a regular point of the function of z if and only if there exists at least one delta such that this f prime z exists for every point which is present inside this neighborhood mode of z minus z0 less than delta. Okay. So in case of complex analysis, since I am considering this neighborhood, it means this neighborhood must represent a disk which is centered at this z0 and having radius delta. So as far as means on the slide onwards, if I am telling a neighborhood, you all will mean that that should be a disk centered at z0 having radius delta unless otherwise stated. Okay. So now see this example. Suppose fz equal to mod z square I am taking, and my student, they all know that this function is only differentiable at z equal to 0. It means if I am considering any neighborhood around this z0, z0 is the only point of differentiability. That is, except this z0, none of the points of this disk is going to be a point of differentiability. That is, here we are not able to get at least one neighborhood in which function is throughout differentiable. Means this z0 which is 0 is not a regular point for this function. So this is an example of a function which is not going to have z0 equal to 0 as its regular point. But now I am telling another example which is not listed here, but one can take fz equal to z. So see, if I am considering any complex number alpha from the unknown plane C, and you construct any neighborhood, and you all know dz by dz is 1, means this z is differentiable. So considering this alpha to be a neighborhood and considering any finite delta which is positive, now centering at this alpha construct any neighborhood, this function is going to be differentiable. And derivative of the function at all those points which are inside this neighborhood is nothing but 1. Means this function is throughout differentiable in any neighborhood of alpha. And since this alpha is an arbitrary point, that means every complex number is going to be a regular point for the function f of z equal to z. Okay. And now I am collecting some notes regarding the collection of all regular points. Let R denote the set of all regular points for a function f of z defined on some domain D. Then obviously this R is going to be an open set. Why, my dear students, this is an open set? See, suppose I am taking this z0, means I am taking, say, z0 is a regular point for the function f of z. It means z0 belongs to R. Since z0 is a regular point, it means I am entitled to have at least one disk centered at this z0 having some radius, say delta. Okay, this will contain z0 by means of the definition itself, and that will be properly contained in the R. Why? Why, my dear students? Because see, every neighborhood of this z0 is also a regular point. Means the entire disk is a disk of regular points. So this disk also contained in R because R is the collection of all regular points. It means this R is open. Okay. So this is the proof that this R is an open set. Now note, a function fz has singular, means the function f of z has a regular point at z0 This implies f z has uncountably many regular points. Why? See, suppose I am claiming that z0 is a point of z0 is a point of regularity for a function f of z. It means centering at this z0, I am entitled to have at least one disk in which f prime z exists. Means f is throughout differentiable. Now you choose any point alpha which is so close to this z0 and maintaining a distance say delta 2. Okay, and this delta 2 is chosen in such a way that this delta 2 is less than delta 1, where this delta 1 is the radius of the disk at which the function is centering at z0. Means the disk is centering at z0 and function is throughout differentiable thereat. Okay. Now see, every such point is going to be a regular point. Why? Because the original disk which is centered at z0 having radius delta 1 is the entire disk of differentiability. So if you choose any radius which is less than this delta 1, means the fast disk. Okay. So this disk is going to be properly contained in the disk which is centered in z0 having radius delta 1. Okay. It means the entire disk is going to have now uncountably many regular points. Okay. It means actually it says that suppose I am claiming that z0 is a regular point. So one cannot claim that there exist only finite number of regular points. Means if I prove that alpha is a regular point, it means this function is now going to have uncountably many regular points, because centering at this regular point alpha, the function is throughout differentiable in the entire disk. So any disk properly contained in this disk, original disk which is centered at alpha, must be proving that every such number in the smaller disk is going to be also a regular point. Okay, that's why this function is going to have uncountably many regular points. Now next. So after summarizing or summing of all these things regarding the regular points for a function f of z equal to w, I am now summarizing the things once more. See, if alpha is a regular point for a function f of z, then around this alpha I am entitled to have at least one neighborhood having radius say delta, in which this function f z is throughout differentiable. Okay, and after knowing all these things, I have collected that the R, which is the collection of all regular points, is going to be an open set. Now reading all these things, I am now focusing on my topic which I have prepared for today. This is the analyticity. So what is analytic functions? So a function f z defined on a domain D is said to be analytic on D if and only if each point of this domain is going to be a regular point. Means every point of domain D is entitled to have at least one neighborhood in which f is throughout differentiable. So this thing is just written here that every point of this D is a regular point. It means f is regular everywhere in D. Or one can simply say that this domain D is an open connected set, and every point is going to be a point of differentiability for the function f of z in D. Okay. So now note, if f is an analytic at z0 means actually there is no such concept of analyticity at a point. Okay. We always talk of the analyticity of a function at or on some domain. Okay. So since here I have already listed for note, so for the sake of understanding, a function f of z is analytic at z0 means there exists at least one open disk around z0 on which this f is analytic. That is, this z0 is a regular point. Now consider a situation that every point of the complex plane is going to be a regular point for some functions. Okay, means every point of this entire plane C is a regular point for a function say f of z equal to w. Then in this case, this function z means f of z is said to be an entire function. That is, if it is analytic in C. Okay. So this is the best example of this function, entire function. One can simply say f of z equal to e to power z is analytic everywhere. And one of the finest and simplest example of analytic or entire function is f of z equal to z. F of z equal to z square. or f of z equal to z cube. So any number of this format z to the power n, where n is a natural number, is going to be an entire function being throughout differentiable in C. Okay. Now, for any complex function of the format, we are traditionally writing this function f of z equal to u plus iv, and if this function is analytic on D, then one should keep the concept in his or her mind that u and v are harmonic functions. Means the nebula operator or the nebula square operator upon u and v are 0, that is nebula square u is 0 and nebula square v is 0. And if this condition holds, means f of z equal to u plus iv is analytic on D, then v is called the harmonic conjugate of u. Then v is called the harmonic conjugate of u. And I am now here introducing one of the best concepts regarding this u and v. One should simply take care of the fact that this u and v are always orthogonal to each other. So this is a note. One can read this note from the book by Panmuswamy and Hartzler. Now, the best part of this talk, means today's best part of the talk, is singularity. So when I am teaching singularity to my students, I am simply asking, suppose you are given a complex number, say alpha, and I am telling fz has singularity at alpha, then tell me the definition. So my students, they generally say that if a function is not regular at alpha, then alpha is said to be a singular point. But it is not the actual case. Only not being regular at alpha does not tell that this alpha is going to be a singularity. Rather, there is an extra case which to be taken simultaneously, that no doubt at this point alpha function is not regular, but it should be regular, means function should be regular in some deleted neighborhood of this alpha. Okay, so simultaneously taking the fact that f is not regular at alpha, as well as f should be regular on some deleted neighborhood of this alpha, tells us that this alpha is a singular point. Okay, so the definition is as follows: if fz is defined on some domain D, subset of C, and z0 belongs to C, is said to be a singular point or a singularity of the function f of z, if fz fails to analytic at z0, but see, it should be analytic, means it should be regular at some point in the neighborhood of z0. Okay, so the examples are here: f of z equal to 1 plus z square plus z, and one can simply verify the fact that z equal to 0 and minus 1 are the points where function is not defined. In fact, this function is not continuous at those points, 0 and minus 1. So not continuity implies non-differentiability. So any neighborhood centered at 0 and minus 1 are not going to be neighborhood of differentiability, and hence not the neighborhood of regularity. That's why this function is nowhere regular. It means this is nowhere singular. Okay, it means this function f of z is singular. So as I told, this z equal to 0 and minus 1 are not going to be the point at where function is continuous. And see, in this definition, I have already written that 0 and minus 1 are the points of singularity. But see, if someone is given or someone has read this definition, he or she might test that the given point is going to be a singular point or not. But by using this definition, one cannot find the points of singularities. So now I am giving another definition which is not listed here. But by means of this definition, one can actually calculate which points are going to be the singular points for this function. Okay. So for this, I am now denoting some notations. Let R be the collection of all regular points. And clearly, this R prime is going to be the derived set of R, that is the collection of all the limit points of this set R. Now, a point alpha belongs to C is said to be a singular point for the function f of z if and only if this alpha is a member of the set of limit points of the set R, but not itself regular. means alpha belongs to R prime but not in R. That is, alpha belongs to R prime minus R. So if S is the collection of all singular points, for the time being I am taking, so in this case S will be R prime minus R. So using this definition, see why 0 and minus 1 are the points of singularity for this function f of z equal to 1 upon z square plus z. See, simply this function is not regular, means this function is not going to be differentiable at the point 0 and minus 1. So the set R will be C minus the double term set 0 and minus 1. And R prime will be C. So S will be in this case R prime minus R, that is C minus 0 minus 1, that is the double term set 0 and minus 1. So by using this definition one can simply calculate all the points of singularities. But see the definition which I have given here, this is the only definition to check whether the given point, if someone gives you some point, that check whether this point is a singular point or not. This can be only verified by means of this definition, but this definition is not going us to this definition is not going to help us to find the singular points actually. Now after doing this example, I have already given another example as f of z equal to 1 upon sine 1 upon z. Also this function is not analytic and has singularity as 0 and 1 upon n pi where n belongs to n. And of course one can take simply here n belongs to z minus 0. Okay, these all points are also going to be the points of singularity. Now note, as to the contrary that we already have known R is the collection of all regular points and this is an open set. But see, singularity is a point which actually contradicts the concept of the regular points for a function of object. Means as like as the R is the collection of all regular points is an open set, and analogous to this, if S is the collection of all singular points, then it should be a closed set instead of open. Okay, and see why I am telling here the fact that suppose for the time being I am taking this fz is having singularity at z0. Okay, so definition says that no doubt if fz is not differentiable, or hence not regular, or one can say not analytic at the point z0, but it should be analytic in some deleted neighborhood of the point z0. Suppose consider a function f of z which is nowhere analytic. Okay, means I am taking the contrapositive part of this statement. Okay, now you know from this to this there is statement P, and this to this as statement Q. Now I am taking negation of Q, means if he is failed to analytic at z0, and also if he is failed to be analytic in some deleted neighborhood of z0. So by law of contrapositivity, one can simply say that this f is not going to have singularity at the point z0. It means the functions which are having singularity, they must be regular in some point or in some interval, or they must have regular points. So one can simply take the conclusion here that nowhere regularity implies nowhere singularity. Okay, the example which I have already given you, that f of z equal to mod z square, this is nowhere regular. Okay, since this is nowhere regular, one can simply say that this is not analytic at anywhere. This is not analytic at anywhere. It means one can simply claim that by if someone leaves this part and say that if f is placed to analytic at z0, then z0 is said to be singular point, then he or she can claim that entire complex plane C is going to be the collection of all singularity for the function f of z equal to mod z square. But this is not, because actual definition is this: it should be nowhere regular. Since fz equal to mod z square is nowhere regular, this means this is nowhere singular. So collection of all singular points for the function f of z equal to mod z square is going to be an empty set. Okay. Now I am again come back to this example, that f of z equal to 1 upon sine 1 upon z, f of z equal to 1 upon sine 1 upon z. This is also going to have singularity at the point 0 and the point 1 upon n pi where n belongs to z minus 0. And I have already said this, Now I classified the singularities in two main branches. So one is isolated singularity and another is non-isolated singularity. So the word isolated itself means that a singularity can be isolated. Means it can be put in a neighborhood where this is the only singularity and the rest of the points of this neighborhood is going to be a regular point. It means if someone able to find at least one neighborhood about a singularity where this singularity is the only singularity in this neighborhood and other points except this point is going to be regular point in some certain domain, then the singularity is called isolated. So one can means the points which are regular except this point now have a chance to count the point that you are not regular. Okay, so this isolate the singularity from all the regular points. Okay, so after knowing the actual concept, now I am defining what is isolated point or isolated singular point. So a point Z0 is said to be an isolated singularity. It means I am going to have at least one deleted neighborhood of this Z0 where rest of the points of this neighborhood are regular points for the function f of z. Okay, so this is the same thing written in here. So if I am going to example one in the last slide, you can simply mean that if I am considering a neighborhood around this point 0 having radius 0 plus 1 by 2, that is half units, then if by taking half unit as radius and constructing a disk centered at this 0, there only 0 is the only singular point for the function f of z, and rest of the points at which the function will be definitely regular. So here this 0 is an isolated singularity, and similar assumptions are similarly we can also able to construct another open disk around this point -1 where -1 is the only singular point. Okay, so in this case I am now entitled to isolate these 2 points by means of taking some delta. So next slide. Now non-isolated singularity. A singularity which is not isolated singularity is called non-isolated singularity. As you all know, means this singularity means any neighborhood. Means if I am taking, suppose I am telling that alpha is a non-isolated singularity. Means if you consider any neighborhood around alpha, okay, if you consider any neighborhood around alpha, in this neighborhood alpha is not only the singularity. With alpha there are infinitely many singular points which are so close to this alpha. Means among those all singular points I am not able to extract out that alpha. Okay, means I am not able to isolate that alpha. That means this is called non-isolated singularity. So for this I am actually giving a simple definition to my friends, to my dear students also. Suppose S is the collection of all singular points. So alpha will be a non-isolated singularity if alpha belongs to S prime, where S prime is the derived set of S. Means S prime is the collection of all limit points of the set of all singular points. I am going to discuss what are the different branches under isolated singularity for a function f of z. It means I am going to discuss classifications of singularity, and this singularity means this classification based on isolated singularity. Isolated singularities are classified under into 3 categories. One is removable singularity, another is pole, and another is essential singularity. So what is a removable singularity? Means suppose I am telling alpha is a singular point for a function f of z. The word removable singularity itself indicates that this singularity can be removed. Means if limit z tends to alpha f of z exists finitely, then one can simply say that this limit as exists finitely, this means this functional value if given to the function exactly, then the function is now going to be analytic instead of maintaining the removable singularity. Okay, and again for pole, if limit means suppose for any point say z equal to alpha is a pole for the function f of z, then limit. So there are two criteria. One is limit z tends to alpha, f of z exists infinitely, means this limit is infinity, and we are able to find at least one natural number which is the smallest, for which limit z tends to alpha, z minus alpha to the power that m into f of z, this is a non-zero finite complex number. So any alpha for the function f of z satisfying these two properties is going to be a pole for the function f of z. Now essential singularity. So what is an essential singularity? The singularity which is not removable as well as not pole is going to be an essential singularity, means limit z tends to alpha f z does not exist finitely, and limit z tends to alpha f z does not exist infinitely. Means by using sequential criterion we are able to find at least two sequences converging to same alpha, but their corresponding functional value sequences may not converge to, means must not converge to f of, means must not converge to same alpha, means same limit. So this limit means the point at which these two conditions hold, means limit z tends to alpha f z is not finite, not infinite, implies this limit does not exist at all, establishing the fact that alpha is an essential singularity for the function f of z. Now next. So as I told, the removable means this this limit z tends to alpha f z exists, and so there are some examples. F of z equal to sin z by z where z is non-zero, f of z equal to cos z minus 1 upon z square, z is non-zero, and f of z equal to z minus sin z upon z cube where this z is non-zero, all have removable singularity at this z equal to 0. And by similar manner I can give you also series of examples by taking this means these 3 can be taken any natural number onwards, 3 means 4, 5, 6. If you take any numbers for this function, this z equal to 0 is going to be a removable singularity. Okay, and there is a no which tells us that we all know that if you consider any neighborhood of removable singularity, the function must be bounded. Okay, so this is an exercise to all of you to verify the fact that in any neighborhood of removable singularity, a function is bounded, means I am entitled to have at least one real number for which the absolute value of the function of z can be bounded. Okay, so this is a theorem in any neighborhood. See, here I am taking any neighborhood. Okay, means for any delta I am taking, and considering this delta as radius centered at any removable singularity, in this neighborhood this function is going to be bounded. Okay, so this is an obvious fact, one can simply verify this. Now next, and already I have told this is 4 because this limit exists infinitely, and there exists smallest m which is a natural number for which limit z tends to, so this is not z, this is alpha, limit z tends to alpha, z minus alpha to the power m f z, this is equal to L, or this value is non-zero finite complex number. Then this alpha means this z naught is said to be pole of m, and if this m is 1, then this pole is said to be simple pole or pole of 1. Okay, and as like as our concept analogous to this removable singularity, we also have in any neighborhood of this pole, every complex function f z must be unbounded. Okay, so if this is bounded, then we may have a blunder by establishing the fact that this should be 0. Why? See, suppose for the time being I am considering in every neighborhood of this pole, okay, the function is not unbounded. So say this function is bounded. It means limit z tends to pole alpha f of z is finite since this is bounded. Okay, so now see here, now construct any sequence say zn which is converging to this pole alpha. Okay, so in this case what I will have, limit n tends to infinity zn minus alpha to the power m f zn. So this is how much, limit n tends to infinity. Since I have already considered the sequence zn is converging to this alpha, so z minus zn must converge to 0. So 0 to the power n will be 0, and this f of zn is bounded as per our assumption. So So this 0 into finite number will be finite, and this finite is 0. So this is not a non-zero finite complex number. That means we are going to violate the second point of definition of code. If we consider this function is bounded in neighborhood of. So our assumption is wrong. It means every function which is code at alpha must be unbounded in every neighborhood of that code. Okay. Now next is essential singularity. As I already told you that this is neither a code nor are universal singularity. Okay. Means limit z tends to alpha or z tends to z0, z does not exist at all. Means it is not existing finitely, not existing infinitely. Okay. So in this case, I have already given a best example. You see here, f of z equal to z sin 1 upon z, where this z is non-zero. But if I am taking this z equal to 0 from the Argand plane, I can simply claim that this z equal to 0 is an essential singularity. Why? Here, in order to prove this, I am going to take the help of sequential criteria. Suppose I am taking two sequences, say one an is 1 by n. By means of this an, I am also able to approach the point 0, as n tends to infinity 1 by n is 0. And if I am taking another sequence I by n, by means of this sequence also I am able to reach this point 0 as n tends to infinity. Okay. So it means I am entitled to have at least two sequences. It means I am already have two sequences. One is 1 by n, another is I by n, which is converging to same testing point of singularity. But see, what is f of 1 by n? Means f of a n is 1 by n sin n, and sin n by n this is 1. And f of bn, that is same thing as f of I by n, and I by n sin n by I, this will be your infinity. Okay. By using L'Hopital's rule, one can simply verify this is infinity. Okay. It means I am able to get two sequences converging to same testing point, but their corresponding function of those sequences is not converging to same number. Means limit z tends to 0, z sin 1 by z. This limit first of all does not exist at all. Okay. It means this function is not continuous. And this also satisfies the definition of essential singularity. So by this fact I can claim that this z equal to essential singularity. And for similar conditions, I am also able to find two sequences. Say for this example of z equal to e to the power 1 by z, I can take two simple sequences. Say one is 1 by n, another is minus 1 by n. By means of 1 by n, I am entitled to reach the point e to the power 0. This is 1, and e to the power minus 1 by n. By this means I can reach to infinity. Okay. So also I am able to get two sequences converging to same testing point, but the corresponding function are two sequences under this function is not converging to the same limit. That's why I am telling this 0 is also a singularity. But do a remark here. Suppose I am considering any function of the format pz by qz, where both pz and qz are polynomial functions of least degree. It means pz and qz are now not going to have any common factors. After deleting all common factors, I am considering pz by qz. And calculate the poles of this function pz by qz. So if I am calculating the poles of pz by qz, then one can simply verify the points which are poles for this pz by qz now going to be an essential singularity for the function e to the power pz by qz. So this is a task for all my friends. So please verify this. And the same condition which is analogous to the pole, one can simply claim that every neighborhood of essential singularity function must be unbounded. Okay. Next. Now there are two statements. One is limit point of zeros of fz is an essential singularity. So this is a true statement. And the statement limit point of poles of fz is non-isolated singularity of an object. But see, my dear, in some books I have read this statement something different. The first statement in some book it is written that the limit point of set of zeros of f of z is isolated essential singularity. But this is a wrong statement. Okay. I am not going to take the names of the books because that could be an so-called derogatory act for them. so I'm not going to I'm not going to tell any such words. But see, in those books it is written that limit point of zeros of fz is an isolated essential singularity. But this is a wrong statement because of the fact that what isolated, what they have written in their books. Okay, so this is not the case because I have example. Simply I have example. Perhaps I have take this example, tan pi by z. Okay, in this case f of z equal to tan pi by z, 0 is the set of, means 0 belongs to the set of zeros of f of z set. But here 0 is not isolated essential singularity. Here 0 is non-isolated essential singularity. Okay, so this is the best counter example to counter the fact that limit point of set of zeros of f of z is an isolated essential singularity. We read the word isolated. Okay, isolated is not the actual statement. We cannot write isolated. Okay, because I am giving this example as counter example to violate the statement, which means this example has 0, which is a non-isolated essential singularity. Okay, but the second statement is a correct statement. It is already as it is written in that book. Okay, but now I am going to discuss what is behavior of a complex valued function at infinity. So to discuss this, we have to construct another function gz and say gz equal to f of 1 by z. And now test the limit of this gz by approaching z to 0. Means calculate limit z tends to 0 gz, that is limit z tends to 0 f of 1 by z. Okay, and if this limit is existing finitely, then z equal to 0 is a removable singularity for the function f of 1 by z, and similarly z equal to infinity is going to be a removable singularity for the function f of z. And if limit z tends to 0 f of 1 by z is a pole, then z equal to infinity is a pole for f of z, and similar condition for essential singularity. Okay, so there are 2 examples or 3 examples to verify that this z equal to infinity has a removable singularity. Here this is an essential singularity, and this is already a non-isolated essential singularity. Now comes to the next one. So there are 2 best modes. So one can simply know that suppose I am given means an entire function, okay, which has 4. Okay, so if this function, this entire function is having a pole at infinity, then we should know that this function, if a pole means if this function, entire function has a pole at infinity, then that function must be a non-constant polynomial, and the order of the pole is same as the degree of the polynomial. And if an entire function has a removable singularity at infinity, then that entire function must be a constant function. Okay, and if I am taking this as example, now I want to verify whether this z equal to infinity is an essential singularity for the function or not. First of all, see, this term which is present here makes the function non-constant. Okay, the term which is present here makes the function non-constant. But see, if this is non-constant, if you take its contrapositivity, so this function is not going to have a removable singularity at infinity, because if it has removable singularity at infinity, it must be a constant. But we have a non-constant. If this is non-constant by law of contrapositivity, this function is not going to have a removable singularity at infinity. Okay, and see again, this is not a polynomial because of the fact this is irreducible, because it has an infinite series expansion of 1 plus z squared by 2 factorial and so on and so forth, plus z squared plus 1 means this entire expression does not have a finite degree, implying this function is not going to be a polynomial. And if I am taking the contrapositivity of this statement being an if and only if statement, if this is not a non-constant polynomial, then this equal to infinity is not going to be a pole. It means I have discarded two cases by taking the contrapositivity of these two facts for this function, that this infinity is not going to be a removable singularity nor a pole, implies or implying that the fact is an essential. So now, as we know that this z equal to infinity is an essential singularity for the function f of z equal to e to the power z plus z square plus 1, by discarding the facts that this z equal to infinity is not a removable singularity and not a pole. Now I am coming forward to my next slide, that on construction of analytic functions and invariant functions. So this is the abstract, and the keynote for this function is analytic functions stimulating or invariant functions constructing complex polynomial functions. Next, single valued function, as we all know, for any input z, if we are going to get only one w, then this function is said to be a single valued function. So for this I can give you a series of examples by taking f of z equal to z mod z square. They all are single valued functions. Now invariant function, if a single valued function f satisfies f of z1 not equal to f of z2 for any 2 points z1 and z2 in some domain G, then f is called a invariant function. So for invariant function, for any invariant function, we should have that function should be a single valued function. So if I am giving you small log z, being this is multivalue, I am claiming that this function cannot be an invariant function, being this is not a single value function. Okay. Now next. So next is some definitions. Let S signifies the collection of functions that are analytic and invariant on G, normalized by the condition f of 0 equal to 0 and f of f prime 0 equal to 1. Also S equal to so this is nothing but the collection of all such functions f from G to C, where f is analytic, invariant on G, f prime 0 is 0 and f of 0 is 1. Now theorem 1 says sum of two invariant functions need not be invariant. So for the time being I am left the proof to all my students to do this, and the theorem 2 says sum or difference of two invariant functions might be an invariant function. So imposing which restrictions or which conditions to take the fact that sum or difference of two invariant functions will be an invariant function. So next slide is there, which says let Gz be any complex coefficient and every term in the polynomial Gz is of degree at least 2, and let Fz is in S, then Gz plus Hz will be in S. Means imposing only this condition that the every term of this polynomial is of at least degree 2, and if f is an invariant function, then sum of these two functions being z or polynomial now going to be an invariant function. Okay, we know sum or difference of two invariant function may not be invariant, but imposing this condition I can able to say this g plus f is going to be an invariant function. And another theorem says let z be a polynomial with complex coefficient such that g of 0 is 0 and g of 0 is g prime of 0 is 2, and let it be any invariant function which is in this set S, then difference of this g and f is now going to be an invariant function. So imposing only this restriction, g of 0 is 0 and g prime 0 is 2 for the function gz, which is a polynomial, and if f is an invariant function, then now this g minus f is going to be an invariant function. So doing all this, I am now summing up the fact that there is no such concept of sum or difference of two invariant functions is univalent, but using this theorem 3 and 4 we can simply construct that, or we can simply say that f plus g or g minus f is going to be univalent or not. So thank you. I am now concluding this one.